Chapter 7 is all about probability. The odds of something happening, experiments, conditional probability, counting principles, all of those good things. Because this does come up in business and in statistics later. So we're going to talk about odds first. So let's think about that. When we toss a coin, it can land one of two ways, heads or tails. If the coin is a fair coin, in other words, it's not rigged, these two possible outcomes have an equal chance of occurring. And we say the outcomes of this probability experiment are equally likely. If we seek the probability that an experiment has a certain result, that result is called an event. So the probability of an event, and you'll see sometimes just a P, this textbook uses a PR to stand for probability of the event, equals the number of times we have successes out of the number of possible outcomes. So, example 1. If we draw a ball from a bag containing 4 white balls and 6 black balls, what is the probability of getting a white ball? Well, it's just as easy as you're thinking. Let me do a different color today. The probability of getting a white ball, so let's abbreviate that with the probability of getting a white, would be, how many are there? There's 4 out of all the possible outcomes. Well, there's 10 all the way in there, so it's 4 out of 10, or 2/5. What about the probability of getting a black ball? Well, probability of getting a black ball. There's 6 of those, and there's 10 possibles, so that's 3/5. What about the probability of not getting a white ball? Well, so the probability of not white would be the same as the probability of getting the black ball in this case, which would be 6 out of 10, or 3/5. Let's go to the next example. If I can turn the page. Alright, sometimes it's hard to know all the possible outcomes. So sometimes it's better to write out what is called a sample space, listing all the numbers, all the possible outcomes. So if we're talking about drawing a card from a box and the cards have been labeled 1 through 12, then this is our sample space, all the numbers from 1 to 12. Each element of the sample space is called a sample point. And an event is a subset of that sample space. Each sample point in the sample space is assigned a probability measure or probability weight, such as the sum of the weights in the sample space is 1. So the probability of getting everything 100%. So the probability of drawing a number at random from them is 1 out of 12, because there's one number and 12 possibles. The event drawing an even number. So the event is a subspace. It's all of the even numbers, 2, 4, 6, 8, 10, and 12. So the probability of drawing an even, each of those is a 1/12. So 1/12, 1/12, 1/12, 1/12. So that's 6/12, or 1/2. So that's the probability of drawing a 2, or a 4, or a 6, or an 8, or a 10, or a 12. Now, some experiments have infinite number of outcomes, but we're going to concern ourselves with ones that we can count. The sample space in which each sample point is equally likely is called an equal probable sample space. So suppose the number of elements in the sample space is little n of s, or little n, with each element representing an equally likely, then the probability for each is 1 out of n, like above, 1 out of 12. So the probability of an event is the number of ways the event can occur out of the number total. Same thing. So if a number is to be selected at random from the integers 1 through 12, what is the probability that it is divisible by 3? So let's think about our event space. Divisible by 3 would be the numbers 3, 6, 9, and 12. So the probability of being divisible by 3 is 4 out of 12. There's 4 options out of the 12 total, so that's 1/3. What about even and divisible by 3? So that's a different sample subspace. Even and divisible by 3 would just be, which one? 6 and 12. So even and divisible by 3. There's only 2 out of 12, so that's 1/6. Even or divisible by 12. Notice the wording's different there. So we're looking for all the even numbers or the ones that are divisible by 3. So we're going to include, so if I'm going down the list, 1, nope, 2, 3 is divisible by 3. And then we have 4, not 5, 6, not 7, 8, 9, 10, not 11, but 12 also. So 1, 2, 3, 4, 5, 6, 7, 8 of them. So the probability of even or divisible by 3. So those words even and or make a big difference. This is taking all the ones that are even and combining them with all the ones that are divisible by 3. 1, 2, 3, oh, that was 8 of them. I lost count there. 8 out of 12, so that would be 2 out of 3. Now, if the probability is certain to occur, like it's definitely going to occur, then the probability of happening is a 1 out of 1. If it's impossible to occur, you're going to get a 0. Any probability is going to be between 0 and 1. It's going to be a fraction or a decimal, always. Now let's look at some sample spaces. Suppose a coin is tossed 3 times. Construct a sample space for the experiment. So what are the ways that we could have a coin tossed 3 times? What could be the results? Well, we could have all 3 heads. We could have 2 heads, then a tail. I could do heads, tails, heads. I could have a tail and then 2 heads. What's the next option? So this was all 3 being heads. These are the ways you could have 2 heads and 1 tail. Then we could have 1 head, 2 tails, or tail, head, tail, or tail, tail, head. Or we could have all 3 come up as tails. So it's a total of 8. So our n of the sample space, the number in the sample space is 8. So that's good to write down. Find the probability of obtaining 0 heads. So the probability of 0 heads. How many different ways was there no heads at all? Well, that only happens once, right? Find the probability of getting 2. So let's look through. One, 2, 3. we can determine probabilities empirically, where the assignment of the probability of an event is derived from our experiences or from data that has been gathered. Probabilities developed this way are called empirical probabilities. It's by viewing an experiment, not by just going, well, what's going to happen? I actually try it out and see what happens, observing the times it happens. And in some cases, that's the only way to assign a probability. With coins, we know how many options there are. Dice, same thing. Cards, same thing. But if I'm looking at other situations, the only way to find it is by experiments. So empirical probabilities may have a theoretical framework, such as tossing a coin. But if we actually tossed a coin 1,000 times, it might come up heads 517 and tails 483. So the empirical probabilities may be a little different, because real life is a little different than in a closed environment. But notice it's close. Okay. The General Standard Company can use information about a large sample of its faucets to compute the empirical probability that a faucet chosen at random will function properly, not leak, for 3 years. Of a sample of 12,316 faucets, 137 were found to fail within 3 years. So what would be the probability that any faucet the company produces will properly work for 3 years? So let's see how many worked. So 137 failed, so we need to figure out how many worked. So 12,316 minus that 137, and that's going to be what? 12,179. So the probability that it's going to not leak is going to be 12,179 out of the total. And most of the time we will end up leaving that. Oops, this calculator doesn't work. Wrong one. Especially when it's the big numbers. Whoops. We'll end up leaving it as a decimal. So I don't want to put it as a fraction. I'm going to let the calculator put that as a decimal. So 0.989. That's a very high probability that the faucets will work. We sometimes use odds to describe the likelihood that an event will occur. Now, odds are a little bit different than probability. So the odds in favor of an event occurring in favor would be the probability of the event divided by 1 minus that probability of the event. And I want you to kind of think about what that means. So the probability that it does occur divided by the probability that it doesn't is really what we have. And usually we state odds as a fraction, or we can say A to B or A colon B. Let's look at a couple of examples of odds. So if the probability of drawing a queen from a deck of cards is 1 out of 13, what are the odds in favor of drawing a queen? So the 1 out of 13 is that it will happen. 12 out of 13 is that it won't happen. So the odds would really be 1 to 12. We could also write 1 to 12 or 1 to 12. What about against drawing a queen? So how many ways could we not draw the queen? 12 ways to 1. So not drawing a queen would be 12 to 1. There are higher odds of not drawing a queen from the deck of cards than there are to drawing a queen. So if we think about what that would be, if to change odds into probability, I would just take that numerator plus the denominator, and that's my total number of events. 1 plus 12 was the total events of 13. So the day after O.J. Simpson was arrested for armed robbery in September 2007, the odds against his being convicted was given in Las Vegas as 6 to 5. What probability of conviction did this indicate? So the odds for being convicted are 6 to 5. So the probability of conviction would be 6 to 11. The probability of not being convicted would be 5 out of 11, which may actually look better as a decimal, because we can think about it as, a percent. 0.545 chance of conviction, and this would be 0.455 chance of conviction. So it's a pretty even odds there.